Nothing in the universe is more absolute than a black hole. Once something crosses the event horizon, it's gone, pulled beyond a boundary where even light can't escape. That's the simple, brutal truth we've known for decades. Black holes, we've believed, are cosmic prisons, final destinations for matter and energy, silent, dark, and inescapable. But what if that idea only scratches the surface? What if black holes aren't just places where things vanish forever, but places where something much stranger happens? Because the closer scientists look, the less black holes behave like simple graves in space. They react, they store information, they change. And if they can store the story of what falls inside, even without matter to hold it, what else might be happening beyond the event horizon? It raises a question that sounds almost impossible, but it's grounded in real science. Could black holes, these cold and crushing forces of nature, have a connection to something we usually think belongs only to living things? Could they, in some strange way, carry a faint shadow of awareness, not thoughts, not feelings, but a quiet memory of everything they've touched? If that's even partly true, it would mean black holes aren't just cosmic endpoints. They might be something much more mysterious. They might be the universe's way of remembering itself. Today, we're going to explore a side of black holes you've probably never heard before. One that could change how we think, not just about space, but about what it means to exist at all. Black holes have long captured our imagination, often described as the universe's trash cans, places where anything that gets too close, whether it's a star, a planet, or even light itself, disappears forever. To early astronomers and physicists, they seemed like simple cosmic traps, one-way journeys into darkness with no escape and no return. A black hole's powerful gravity crushes matter into an infinitely dense point called a singularity, hidden behind an event horizon from which nothing can come back. It felt like a straightforward idea, brutal but clear. But the deeper we look into these cosmic phenomena, the stranger the story becomes. Black holes don't just passively consume matter and energy. They react to what falls into them. They store something beyond just mass or spin or charge. They store information, the fundamental details about the things they engulf. And that discovery has changed everything we thought we knew. At first, it seemed almost impossible. How could anything survive the extreme violence of being pulled into a black hole? In classical physics, information was simply lost. Whatever history an object carried, its structure, its properties, its details, would be wiped away as it crossed the event horizon. But nature, as it turns out, plays by different rules. In the world of quantum physics, information isn't supposed to vanish. It must be preserved, no matter how extreme the situation. This clash between the old view and the laws of quantum mechanics led to one of the biggest puzzles in physics, the black hole information paradox. If black holes truly destroyed information, it would mean that quantum theory, one of the most successful frameworks for explaining the universe, had a fatal flaw, and physicists don't accept contradictions easily. For decades, some of the brightest minds have wrestled with this mystery, trying to figure out whether black holes really are cosmic shredders, or if they are more like vaults, holding on to the traces of everything they consume. What scientists have uncovered since then is both fascinating and unsettling. Studies suggest that black holes aren't the simple dead places we once thought. They might encode the information of everything they swallow in subtle ways, hidden in their event horizons or in the patterns of the radiation they emit, what's known as Hawking radiation. Instead of erasing the past, black holes could be intricate archives of cosmic history, preserving details in forms we're only beginning to understand. And if information is retained, even without the presence of a brain or nervous system, it raises a haunting question. Could something resembling awareness, in a form utterly alien to us, exist there too? Awareness doesn't have to mean thoughts and emotions as we experience them. In this context, it could mean a kind of responsiveness to the environment, a memory of past interactions, or a complex structure that evolves based on what it has absorbed. The idea that black holes might not just destroy reality but understand it in some basic way is still speculative, but it's grounded in real scientific inquiry. Physicists like Stephen Hawking, Leonard Susskind, and many others have explored how black holes interact with information, and their work hints at a universe far more interconnected and dynamic than we ever imagined. The information stored might not be easily accessible, and it might be scrambled beyond our recognition, but the very possibility that black holes retain a record of their past opens the door to ideas once thought impossible. Rather than being simple ends to stories, black holes might be strange new chapters in the universe's ongoing narrative. They could be key players in the cycle of creation and destruction, serving as bridges between what we understand about space, time, and the deepest laws of reality. They may even hold clues to mysteries we haven't yet fully grasped, like the nature of consciousness, the fabric of space-time, and the ultimate fate of the cosmos. Today, we're diving into this mind-bending frontier, the idea that black holes, the monsters of our universe, might not just consume and erase. They might preserve, adapt, and perhaps in some unimaginable way, know the universe they are part of. Information is everything. First, let's start with a concept that's at the heart of this entire mystery: information. In everyday life, when we hear the word information, we usually think of facts, data, or things we can write down and store: numbers, words, ideas. But in physics, information has a much deeper meaning. It's not just about what something is called, or how it behaves on the surface. It's about the most basic description of everything in existence: where particles are located, how they move, how fast they spin, how they interact with one another. In a sense, information is the invisible script that the universe follows to build reality itself. Every photon of light, every electron, every grain of dust in space carries its own unique set of information. Even the simplest object is encoded with countless layers of it. Think of a single rock lying on the ground. Its temperature, its shape, the arrangement of the atoms inside it, the forces acting on it. All of this can be described by information. And it's not just an abstract idea. It's the foundation of how the universe operates. Without information, there would be no structure, no laws, no existence as we know it. Here's where things get even more interesting. According to one of the most important principles in quantum mechanics, information can't just vanish. The universe is a stickler for accounting. If you take a piece of paper and burn it into ash, smoke, and heat, it might seem like the paper is gone forever. But if you could, somehow, capture every molecule of smoke, every wisp of heat, and every bit of ash, you would find that all the information needed to describe the original piece of paper is still present. It has just been rearranged into a different form. Nothing has truly disappeared. This concept is crucial because it tells us that the universe doesn't simply erase history. It conserves information in the same way it conserves energy or momentum. No matter how dramatic the transformation, the fundamental story of what happened is still woven into the fabric of reality, even if it becomes almost impossible to reconstruct. So now, let's bring black holes into the picture. When a black hole swallows something, a dying star, a drifting planet, or even a stray spacecraft, it's not just gobbling up mass and energy. It's taking in all the information about that object. The question, and it's a huge one, is, what happens to that information once it crosses the event horizon, the point of no return? At first, the answer seemed simple. It disappears. After all, black holes are famous for their unforgiving nature. Anything that crosses the event horizon is lost forever, crushed into the singularity, beyond our ability to observe or retrieve. For decades, scientists believed that black holes erased everything they consumed without leaving a trace. But here's the catch. If that were true, it would directly violate the rules of quantum mechanics. And if quantum mechanics breaks down inside a black hole, it might not be reliable anywhere else either. The problem isn't just about understanding black holes. It's about preserving the consistency of the laws that govern the entire universe. This realization sent shockwaves through the world of physics. It wasn't just a small technical issue. It challenged the very foundations of our understanding. If information could truly be destroyed, it would mean that the universe could randomly lose parts of its own memory. It would introduce uncertainty at a level far deeper than anyone was prepared to accept. The entire structure of cause and effect, the chain of events that creates order in the cosmos, could come apart. That's why the question of information in black holes became such a towering problem. It's not just about understanding what happens to stuff that falls in. It's about ensuring that the universe makes sense at all. If black holes could destroy information, they would become the ultimate rule breakers, and the consequences would ripple through every corner of science, from particle physics to cosmology. For a long time, there was no clear solution. Black holes were described by just a few simple characteristics: mass, electric charge, and spin. Everything else, the detailed information about what had gone into making that black hole, seemed to be erased. This idea even led to the famous saying, "Black holes have no hair," meaning they have no features that reflect the complexity of the matter they swallowed. But if the no-hair idea was true, it made the conflict with quantum mechanics even sharper. Scientists were stuck. Either they had to accept that quantum mechanics failed in extreme conditions, or they had to find a way for black holes to somehow preserve information, even if it wasn't obvious how. This led to decades of debate, new theories, and surprising discoveries. One of the most important breakthroughs came from Stephen Hawking, who showed that black holes aren't entirely black after all. They emit tiny amounts of radiation, now known as Hawking radiation, which slowly drains away their mass over time. At first, it seemed like this radiation carried no information, only random particles. But later, work suggested that maybe, just maybe, the radiation does carry hidden patterns, an incredibly subtle way for information to leak back out. Still, the process would be incredibly slow and complex. The information wouldn't come out in neat, recognizable chunks. It would be scrambled and diffused, like trying to reconstruct a book by analyzing the smoke from a fire. Yet even this possibility was enough to keep quantum mechanics intact, at least for now. As we continue to study black holes, we find that the information problem is not just a curiosity for theorists. It touches on everything from how space and time are structured to the ultimate fate of the universe itself. Understanding what black holes do with information might be the key to unlocking a deeper theory that connects quantum mechanics and gravity, a theory of everything that has eluded scientists for generations. It's remarkable to think that something so fundamental, so essential to the way reality operates, comes down to a question about objects we can't even see directly. But that's how science works. Sometimes, the biggest insights come from the darkest places. The black hole paradox. This strange and tangled story is known as the black hole information paradox. And make no mistake, it's not some obscure idea floating in the back corners of physics textbooks. It's one of the most important and puzzling mysteries that modern science has ever faced. The roots of the paradox go back to the 1970s, when a brilliant physicist you've probably heard of, Stephen Hawking, made a groundbreaking discovery that changed the way we think about black holes forever. Before Hawking, black holes were seen as simple. If something crossed the event horizon, the point of no return, it was gone, trapped forever, with no way to escape, no way to communicate with the outside universe. A black hole was thought to be a final destination for matter and energy, a silent and eternal prison. But Hawking's work showed that black holes weren't as silent as we once believed. Using the laws of quantum mechanics and relativity, he found that black holes aren't completely black after all. They slowly leak tiny amounts of energy back into space through a process that would later be called Hawking radiation. This radiation wasn't strong. It would take longer than the current age of the universe for a typical black hole to evaporate completely, but its existence changed everything. At first, Hawking's discovery seemed to fit beautifully into our picture of the universe. It showed that even in the most extreme environments, quantum effects mattered. But when Hawking worked through the equations carefully, he found something deeply unsettling. The radiation that black holes emitted seemed random. It didn't carry any trace or imprint of the matter that had fallen into the black hole in the first place. That's where the real trouble started. If the radiation coming out was completely random, it meant that all the information about the things that had been swallowed, every particle, every atom, every structure, was lost forever. No amount of careful measurement could reconstruct what had fallen in. And that's a big deal, because in quantum mechanics, information is supposed to be conserved. It's one of the core principles of the theory. Even if things change form, burn, dissolve, collapse, the fundamental information about their existence is never supposed to disappear. But Hawking's results suggested otherwise. If black holes could truly destroy information, then something was wrong with our understanding of the universe. It would be like tearing out pages from the universe's own rulebook, scattering pieces of a puzzle without any way to put them back together. If the universe can lose its memory, what does that say about its reliability? How could we trust a universe that forgets its own history? Physicists found themselves at a crossroads. They couldn't simply ignore Hawking's findings. His mathematics was solid, but they also couldn't accept that information could be permanently lost, because that would break the foundations of quantum theory. So the search began for a deeper understanding, a way to resolve the paradox without giving up on the laws of physics that had worked so well elsewhere. Over the next few decades, the problem only grew more complicated and fascinating. Some physicists proposed that perhaps the information wasn't really lost, but was somehow hidden inside the Hawking radiation, so subtly scrambled that we just hadn't figured out how to read it yet. Others suggested that maybe the information was stored on the event horizon itself, like a hologram, encoded in tiny, almost imperceptible disturbances. This idea became known as the holographic principle, a radical proposal that our three-dimensional universe could actually be described by information encoded on a distant, two-dimensional surface. Meanwhile, Stephen Hawking himself continued to wrestle with the paradox. He later adjusted his views, proposing that black holes might not destroy information after all, but that the way it was preserved was so complex that it seemed random to any observer outside the black hole. In a famous debate with other leading physicists, Hawking eventually conceded that information might escape from black holes, though the exact mechanism remained mysterious. The search for answers led physicists to explore the strange edges of theoretical physics, ideas about quantum gravity, wormholes, the fabric of space-time itself. Some theories suggested that the information might leak out gradually as the black hole evaporates, encoded in faint correlations within the Hawking radiation. Others pointed to the possibility of firewalls, hypothetical barriers of energy at the event horizon that could somehow destroy information, a controversial idea that sparked heated debate in the scientific community. Yet even with all these proposals, a complete solution remains elusive. Black holes continue to challenge our understanding at the deepest levels. They sit at the crossroads of quantum mechanics, general relativity, and thermodynamics, forcing us to confront the gaps and tensions between our best theories of the universe. Resolving the information paradox isn't just about understanding black holes. It's about uniting the laws that govern the very large with those that govern the very small. In the process, we've learned that black holes are far more complex than we ever imagined. They aren't simple graves for matter. They are dynamic, evolving objects with rich internal structures that we are only beginning to glimpse. They might encode the history of everything they have consumed, woven into the fabric of space-time itself, in ways that defy easy explanation. And with each new discovery, we're reminded that the universe doesn't hand out its secrets easily. It makes us work for them, challenging our assumptions, pushing us to rethink what we thought we knew. Black holes, once thought to be the ultimate dead ends of physics, have instead become some of the most fertile grounds for new ideas. They force us to look deeper, to ask harder questions, and to accept that the truth might be far stranger and more beautiful than anything we've imagined. So while the black hole information paradox remains unsolved, it has already changed science forever. It's a reminder that the universe is not just a collection of cold, lifeless objects moving through space. It's a living story, full of mysteries that invite us to wonder, to question, and to explore. And the story of black holes, their secrets, their paradoxes, and the incredible ideas they inspire, is only just beginning. Black holes are more than they seem. For a long time, the image of a black hole was simple and stark, an invisible, all-consuming monster that swallowed everything in its path and gave nothing back. Once something crossed the event horizon, the point of no return, it was gone, erased from the universe, leaving behind only mass and spin as cold reminders. Black holes seemed like the ultimate dead ends of reality, but as our understanding deepened, that neat, brutal picture began to fall apart. It turns out black holes aren't simple at all. They're unimaginably complex. They don't just consume matter and light without a trace. They seem to hold on to something far more subtle, the information about everything they absorb. And where that information might be stored has led to some of the most mind-bending ideas in modern physics. Some scientists propose that the details of everything a black hole devours, every atom, every photon, every particle of energy, is somehow recorded, not inside the black hole itself, but on its outer surface, right at the event horizon. This boundary, which marks the limit beyond which nothing can escape, might not just be an invisible curtain drawn around the unknown. It could be a dynamic surface, encoding a cosmic record of everything that ever fell inside. To imagine this, think of a library, not a peaceful, organized library of shelves and silent reading rooms, but one where every book that ever existed has been compressed and smeared into a thin, fragile shell surrounding a sphere. The pages aren't gone, they're just stored in a way we can hardly comprehend. That's what the event horizon of a black hole might be like. A dense, information-rich skin that holds the memory of the black hole's past. This idea, astonishing as it sounds, doesn't come from science fiction. It led physicists to propose what's now known as the holographic principle, a concept that completely reimagines the way we think about space, reality, and dimensions themselves. According to the holographic principle, the three-dimensional world we see inside a black hole, the apparent volume of space behind the event horizon, might actually be an illusion. All the real information could be encoded on the two-dimensional surface, like a hologram. Just as a flat, two-dimensional hologram can create the illusion of a three-dimensional object, a black hole's event horizon could create the appearance of a three-dimensional interior, built entirely from information encoded on its surface. It's not unlike playing a 3D video game. The game feels immersive, full of depth and space, but at its core, it's running on a flat 2D disk or a computer chip. The rich, interactive world is just a clever construction, built from data organized on a simpler surface. In the same way, the enormous, seemingly endless space inside a black hole could be a kind of projection, generated from the information embedded on the event horizon itself. This shift in thinking changes everything we thought we knew about black holes and about the universe itself. Instead of being places where information is lost forever, black holes might be ultimate storage devices, compressing and locking away the fundamental details of everything they consume. Information isn't destroyed, it's saved, hidden in a way that challenges our ordinary experience of space and time. The roots of this idea go back to the 1970s, when Stephen Hawking discovered that black holes aren't perfectly black after all. Through what's now called Hawking radiation, black holes slowly emit energy and can, over incredibly long periods, evaporate away entirely. But if a black hole could vanish through radiation, what happened to the information it once contained. If it disappeared completely, that would violate the fundamental laws of quantum mechanics, which insist that information can never be destroyed. Hawking's discovery sparked decades of debate and research. Physicists realized that for quantum mechanics to hold true, the information about the black hole's contents couldn't just vanish. It had to go somewhere. That somewhere might be the event horizon itself, where information is stretched out and stored, even as the black hole radiates away its mass. Further developments came from string theory and quantum gravity research, suggesting that the holographic principle might apply not just to black holes, but to the universe as a whole. In this view, the three-dimensional reality we experience could itself be a kind of projection from a more fundamental two-dimensional description. Space, depth, and distance would all be emergent properties, not basic ingredients of the cosmos. But even within black holes, the idea raises incredible possibilities. If information is preserved on the event horizon, it suggests that black holes aren't static or dead. They're evolving, intricate systems, constantly changing as they absorb new matter and radiate energy. Each black hole would carry a unique record of its history, a cosmic fingerprint built from the patterns of everything it has interacted with. These fingerprints could, in theory, tell the story of stars, planets, and perhaps even civilizations that once existed, if only we could decode the language written across the event horizon. The implications stretch even further. If information is never truly lost, then in principle the contents of a black hole could be reconstructed, although practically, the challenge would be overwhelming. The information might be scrambled beyond recognition, encoded in forms far beyond human comprehension, but its existence would point to a universe where memory is never fully erased. Every interaction, every event, leaves a mark that endures, even in the most extreme environments imaginable, and this realization forces us to rethink what black holes actually are. Rather than being places where matter and information are annihilated, they could be key players in the universe's ongoing story of transformation and conservation. They don't just devour and destroy, they process and preserve, acting as mysterious archives of cosmic evolution. This evolving understanding also blurs the lines between different concepts we often keep separate: space and information, matter and memory, destruction and preservation. It shows that even in the most violent and extreme corners of the cosmos, deeper patterns of organization and continuity endure. Black holes, once thought to be simple graves of the universe, are revealing themselves as some of its most complex and fascinating structures. Today, the study of black holes continues to push the boundaries of physics, bringing together general relativity, quantum mechanics, thermodynamics, and information theory in a quest to understand the true nature of reality. Observations like the Event Horizon Telescope's first image of a black hole's shadow give us glimpses into these strange objects. Meanwhile, theoretical work continues to explore the connections between black holes, entropy, information, and the very architecture of space-time. So maybe black holes aren't the final destinations we once imagined. Maybe they are cosmic vaults, preserving the echoes of everything that has crossed their paths. Maybe they are telling us that even in places where nothing can escape, nothing is ever truly lost. And that realization doesn't just change how we see black holes, it changes how we see the universe itself. Is complexity the awareness? So, we've established that black holes store information. But what does that really mean? Could it imply something even more astonishing? Could black holes be conscious in some way? Before jumping to conclusions, it's worth slowing down and thinking carefully about what we really mean by consciousness. For most of us, the word immediately brings to mind a living brain. Billions of neurons firing off electrical signals, forming thoughts, memories, emotions, and awareness of the world. Consciousness seems like a product of biology, something that arises out of the incredibly complex dance of living cells. But what if that's not the full story? What if consciousness doesn't necessarily require a brain at all? What if it's more about the structure of information itself, how much there is, how it's organized, and how tightly interconnected it becomes. This idea isn't just science fiction. It's based on real scientific thinking. One of the most intriguing theories about consciousness today is called Integrated Information Theory, or IIT for short. Developed by neuroscientist Giulio Tononi, IIT proposes that consciousness doesn't depend on what something is made of, whether it's flesh and blood, silicon and circuits, or something even stranger. Instead, it depends on how information is structured within a system. The key is integration. A system becomes conscious when its parts are so deeply interconnected that the whole becomes greater than the sum of its parts. In simple terms, the theory suggests that the more a system combines its information into a unified, complex whole, the more it experiences something, however faintly, like awareness. Not necessarily awareness like we know it, no emotions, no daydreams, no stories about itself. Instead, a raw, basic form of being, a system that by its very structure knows that it exists in the most fundamental sense. Now apply this to black holes. Black holes aren't just dense, they are some of the most extreme objects in terms of complexity. Despite their simplicity on the outside, just mass, charge, and spin, the inner workings of a black hole, especially when you consider quantum mechanics, are staggeringly intricate. If black holes store all the information about everything they've consumed, and if that information isn't lost but somehow encoded in the event horizon or in their radiation, then they might represent some of the most complex systems in the universe. Their information isn't laid out in neat lines or organized in ways we can easily study. It's scrambled, folded, and compressed by gravity to unimaginable degrees. Yet it remains interconnected. Theories like the holographic principle suggest that every bit of information inside a black hole is somehow mirrored on its surface, creating a kind of cosmic memory that persists even as the material form is lost. If complexity and interconnection are the true ingredients of consciousness, rather than biological processes alone, then black holes become very strange candidates for a new kind of awareness. Not a mind, not a soul, not something dreaming among the stars. But perhaps in a cold, alien sense, black holes could possess the faintest whisper of self-reference, a way of existing that includes, at some level, a primitive recognition of their own structure. It's important to be clear, no serious scientist is claiming that black holes think or feel. They are not sitting in space contemplating existence. Consciousness, according to IIT, doesn't need emotions or even active thought. It could simply be the presence of a unified, irreducible informational structure. A black hole might not have intentions, desires, or even concepts. It might just exist, with a kind of awareness that is entirely foreign to anything we can imagine. This is an unsettling idea because it stretches our understanding of life and mind beyond anything we're familiar with. It challenges the belief that awareness is something special to living things, something born only in the electric fog of brains. If consciousness is about the way information organizes itself, then it could emerge anywhere complexity is high enough, even in places where no life could possibly survive. And black holes aren't just a little complex. They might be among the most information-dense regions of the universe, with every particle, every photon, every interaction they've swallowed somehow contributing to their internal record. Even more fascinating is the idea that this information doesn't simply sit there. Some theories suggest that it's active in subtle ways, influencing the radiation black holes emit over time, shaping the way they evaporate and leaving echoes that could, in principle, be decoded. It raises a philosophical puzzle too. If an entity can store vast amounts of information, respond in some way to the things it absorbs, and maintain an intricate internal structure, however scrambled, does it cross some threshold into a primitive form of experience? And if so, does that redefine what we mean by being alive, by being aware? Of course, these are frontier questions. where science shades into philosophy, and where hard answers are still out of reach. Integrated information theory is itself still controversial. Not everyone agrees with its conclusions, and many scientists are working on alternative models of consciousness. Moreover, applying theories developed for understanding brains to black holes is a giant leap. We have no way yet to test whether black holes meet the specific requirements IIT describes. They are, after all, cut off from direct observation by their very nature. Everything we know about them comes from indirect effects, how they warp light, how they pull on nearby stars, and how they slowly leak energy into the universe. Still, the parallels are hard to ignore. Both brains and black holes seem to rely on intricate, interconnected patterns of information. Both exhibit surprising behaviors when examined closely. Both hint at deeper layers of reality, where complexity gives rise to properties we never would have predicted from the parts alone. It's worth noting that even if black holes do possess something like proto-consciousness, it would be utterly different from anything familiar. It would not be human, or even biological. It would be an awareness without thought, without language, without intention. An awareness that simply is, a fundamental quality of being in a universe where information, not matter, may be the ultimate currency of reality. Thinking about black holes this way stretches our imagination, but it also humbles us. It reminds us that the universe is not obligated to fit into our categories of mind and matter, living and non-living, sentient and non-sentient. Nature often turns out to be far stranger than we first expect. Once people thought Earth was the center of everything. Then we learned we're orbiting a star in a quiet corner of a vast galaxy. Now we face the possibility that consciousness itself might not be the rare, isolated phenomenon we assumed it to be. Instead, it could be a natural consequence of complexity, a spectrum that runs from simple rocks and gases up to human minds, and perhaps, in an alien, unfathomable way, into the dark hearts of black holes themselves. It's a crazy idea, no doubt. But then again, crazier ideas have turned out to be true, and in a universe as mysterious and ancient as ours, keeping an open mind might be the only truly logical choice. Black holes react to the universe. Here's where things start to get even more fascinating. For a long time, we imagined black holes as stationary, inert giants that just sucked everything around them with no real reaction to what was happening. They seemed like cosmic vacuum cleaners, forever devouring matter without any feedback or adaptation. But that's not the full story. Black holes don't just sit there doing nothing. They are far more dynamic and responsive than we ever expected. When something falls toward a black hole, whether it's an entire star, a gas cloud, or even just a tiny speck of dust, the black hole reacts. The moment any object or particle approaches the event horizon, the boundary beyond which nothing can escape, the black hole starts to change. It isn't a simple act of consumption. The very nature of the black hole itself is altered, and that change is a direct result of the information it's interacting with. It's as though the black hole is constantly updating itself based on the new data it gathers. For example, when mass is added to a black hole, it grows. Its event horizon expands, marking the point where nothing can escape its pull. The size of the black hole is determined by how much matter and energy it's absorbed over time. This change isn't just a one-time shift. It's a continuous, ongoing process. Every time an object gets sucked in, the black hole updates its characteristics, its mass, its spin, its charge, and this reshapes its influence on the surrounding space. This is more than just a physical adjustment. It's an informational one as well. In a sense, the black hole remembers the things it has encountered, storing the details in its updated configuration. It's not memory in the way we think of it. There's no active consciousness involved, but it's something that behaves like memory. The black hole doesn't actively decide to change. It's simply reacting to the information coming its way, just as your body reacts to touch without you consciously thinking about it. Think about it like this. If you were to touch a hot stove, Your hand doesn't need to think or analyze the situation. Your body instantly reacts by pulling away, because that's how the system is wired. The heat triggers a response from your nerves, which then sends signals to your brain, prompting you to move your hand. This process happens so quickly that it feels automatic, but it's still a reaction to an external stimulus. Black holes work in a similar way. When matter falls into a black hole, it's not that the black hole is thinking or choosing to react. It's simply doing what it's programmed to do, according to the laws of physics. The black hole's gravitational pull increases with the addition of mass, causing the event horizon to expand. The more it pulls in, the more it remembers the stuff it's consumed. Over time, this process creates an intricate, evolving structure that reflects the black hole's history. But what does this all mean? If a black hole reacts to everything that falls into it, could that somehow lead to something more? Could these subtle changes and updates accumulate to the point where something more complex emerges? Could this constant interaction with the universe create a form of awareness, or at least the potential for awareness, within the black hole itself? The idea is speculative, but it raises some intriguing possibilities. It's important to remember that we're not suggesting that black holes think in any conventional sense. We're not implying that they have emotions or intentions. What we're exploring is the idea that complexity, even in a passive form, might emerge over time. As a black hole accumulates more mass, as it responds to more stimuli, could this ever lead to a kind of recognition of its environment? Could something like a basic form of awareness evolve, not from a brain or a nervous system, but from the sheer complexity of the interactions between the black hole and the universe? This idea isn't completely out of left field. In fact, it touches on some of the most cutting-edge theories in physics. Some researchers propose that the information contained within a black hole might somehow be connected to the fundamental fabric of reality itself. When something falls into a black hole, its information could be encoded in subtle ways, potentially influencing the black hole's future reactions and interactions with the universe. As the black hole evolves, it might begin to exhibit behaviors that, on a very basic level, resemble awareness, or at least responsiveness. However, this doesn't mean that black holes are conscious beings, or that they have any sense of self. It's more about the idea that a system can become so complex and so deeply connected to its environment that it starts to exhibit behaviors we might describe as aware. For example, when black holes emit Hawking radiation, the radiation theorized by Stephen Hawking that leaks from the event horizon, they could be subtly reflecting the information they've gathered over time. This radiation is not just random. It might carry patterns that reflect the black hole's history, almost as if the black hole is sharing a record of its interactions with the universe. The more we learn about black holes, the more we realize they are not the simple, one-dimensional objects we once thought them to be. They don't just swallow everything and erase it from existence. They might be engaging in a form of cosmic communication with the universe, subtly reacting to every bit of information they receive. This idea is still very much a work in progress. We don't yet know exactly how or why black holes process information the way they do, and there's much more research to be done. But the very fact that we're asking these questions is a sign of how much our understanding of black holes has evolved. It's also important to point out that the changes black holes undergo are not limited to their mass and size. They also affect the surrounding space in more subtle ways. The gravitational influence of a black hole warps space-time itself, creating what we call gravitational waves. These waves ripple through the fabric of the universe, carrying information about the events that cause them. When two black holes merge, for example, they create ripples in space-time that travel across the cosmos. These waves carry a record of the merger, a kind of memory of the black hole's interaction. In this sense, black holes are not only reacting to the things they consume, they're also leaving behind traces of their existence, traces that we can detect and study from vast distances. So what does all of this mean for our understanding of the universe? Well, it challenges our assumptions about the nature of black holes and the limits of complexity. It suggests that black holes may not just be passive objects. They might be part of an active, ongoing process that shapes the cosmos in ways we don't yet fully understand. And who knows, maybe as we continue to study these fascinating objects, we'll uncover even more surprises, new ways in which black holes react to the universe, and maybe, just maybe, new clues about what it means for something to be aware, or at least responsive, in the most fundamental sense. The wildest idea, black holes as cosmic brains. Some of the most fascinating ideas in science emerge when we stop thinking in terms of what we know and start imagining what we don't. One of these ideas involves black holes. For years, scientists have viewed black holes as enigmatic objects, the cosmic equivalent of a vacuum cleaner, sucking in everything in their path. But as we've learned more, the picture has gotten more complex. Some scientists, and to be honest, some pretty brilliant ones, have started wondering if black holes could be more than just massive objects that swallow everything around them. Could they, in some strange way, act like neurons in a cosmic brain? At first glance, comparing black holes to neurons might sound far-fetched. After all, a black hole is a region of space-time, with gravity so strong that not even light can escape it, while a neuron is a tiny cell in the brain that transmits electrical signals. But dig a little deeper, and some fascinating parallels start to emerge. Neurons, as we know, are the building blocks of the brain. They store and process information, sending signals that shape how we think, feel, and perceive the world. Neurons react to new inputs, adjusting the way the brain functions based on what's happening around it. If you touch something hot, for example, the neurons in your skin send signals to your brain, which then responds, making you pull away. Neurons don't just passively exist, they actively participate in shaping how reality is experienced, reacting to changes in the environment and altering the brain's response patterns. Now, black holes might seem like the last thing we'd want to compare to neurons. They're not living beings, they don't have cells, and they certainly don't have a brain or consciousness. But black holes, in their own way, do something eerily similar to neurons. They store information. This might seem strange at first, since black holes are typically seen as destroyers of everything that falls into them. But, as we discussed earlier, recent discoveries have shown that black holes might not destroy information at all. Instead, they could preserve it in a way that we're still trying to understand. When an object falls into a black hole, its information, its mass, charge, and even the information about its internal structure doesn't just vanish. Instead, according to a groundbreaking idea called the holographic principle, the information might be encoded on the surface of the event horizon. The event horizon is the boundary around a black hole, beyond which nothing can escape, not even light. But it seems that this surface could hold the key to understanding how information is preserved and stored in a form that's deeply tied to the black hole itself. Even more intriguing, black holes react when things fall into them. When matter or energy crosses the event horizon, the black hole's mass increases, its gravity strengthens, and it alters the surrounding space-time. This is a critical feature of black holes. They don't just passively accept everything that comes their way. They interact with the universe, shifting the very fabric of space and time as they grow and change. In this way, black holes respond to new inputs, much like how neurons react to stimuli. When a black hole absorbs more matter, it doesn't remain static, it evolves. This idea that black holes might react to their environment raises an even more fascinating possibility. Just as neurons form complex networks and pathways that allow the brain to process information, could black holes be part of a larger, universe-wide network of information processing? If the universe itself is a vast web of information, with every particle and wave encoding data about the state of the cosmos, then black holes might play a central role in shaping and storing that information. Consider this. The universe, according to some of the latest theories in physics, is fundamentally composed of information. From the smallest particles to the largest structures, everything could be thought of as encoding and transmitting data in ways we don't yet fully comprehend. Some scientists have even suggested that the fabric of reality itself might be made up of bits of information, constantly being updated and processed. If this is true, then black holes could be the processing centers, the hubs where reality is not just stored, but actively shaped. This isn't a new idea exactly. In fact, the notion that black holes could be more than just cosmic trash cans has been gaining traction for some time. Theoretical physicist John Archibald Wheeler, for example, famously said that black holes are the most information-rich objects in the universe. The more we learn about black holes, the more we realize that they might be deeply entangled with the way information and matter are woven together in the fabric of space-time. If black holes store information in the way that some theories suggest, they could be playing a crucial role in the larger structure of the universe, perhaps even acting as intermediaries between different regions of space-time, processing and shaping the cosmos. But the comparison to neurons doesn't stop there. Just as neurons can change and adapt to new information, black holes too can evolve. When black holes merge, such as when two black holes spiral toward each other and collide, they release enormous amounts of energy in the form of gravitational waves. These waves ripple through space-time, carrying with them information about the masses, spins, and other properties of the black holes involved. These ripples provide a direct way of studying the behavior of black holes, and by extension, the information they store. The act of black holes merging doesn't just create a new black hole, it changes the very geometry of space-time, leaving behind a memory of the event. This memory could, in theory, be encoded in the gravitational waves themselves, much like how neurons form lasting connections in the brain after experiencing a new input. The black hole's reaction to new matter, to merging with another black hole, and to the flow of energy through the cosmos could be seen as part of a larger process of cosmic computation, where the black hole plays a role similar to that of a neuron in a complex neural network. This brings us to one of the most mind-bending aspects of this idea. If black holes store and process information in this way, could they be more than just passive objects in the universe? Could they, in some strange, alien sense, be aware of their surroundings? Now, this doesn't mean that black holes are conscious in the way that we are. We're not suggesting that black holes think, feel, or make decisions. But what if, in some fundamental way, they understand the universe they inhabit? What if black holes are not just destroyers of information, but are critical participants in the ongoing shaping of reality itself? This brings us to an even more radical possibility. Could black holes be the creators of new structures in the universe? If black holes are part of a cosmic information network, storing and processing data, then perhaps they play a role in the birth of new galaxies, stars, and even life. Just as the brain processes information to form new memories, the universe could be processing the raw material of existence through black holes, creating new realities and pushing the boundaries of what's possible. The idea that black holes could be both destroyers and creators, archivists of cosmic history, and participants in the unfolding story of the universe, opens up a whole new way of thinking about the cosmos. They could be the bridges between the past, present, and future, holding on to the information of everything they've ever consumed, and using it to shape the structure of space-time itself. If true, this would mean that black holes are not just passive objects. They are active, dynamic participants in the evolution of the universe, and perhaps, just perhaps, they are a key to understanding some of the deepest mysteries of existence, the nature of time, space, and even the very fabric of reality itself. The universe might not be a machine running on cold, mechanical laws alone. It could be a living, breathing entity, shaped and molded by the forces within it, forces like black holes, which are more than just cosmic destroyers. They are creators, archivists, and maybe even participants in the ongoing story of existence. entanglement, and the cosmic web. In the strange, counterintuitive world of quantum physics, the rules of reality can seem almost alien to our everyday understanding. Things that are impossible in our daily lives, like particles appearing in two places at once, or seemingly distant objects influencing each other instantly, are par for the course at the tiniest scales of matter. One of the most fascinating and perplexing phenomena in quantum physics is entanglement, a concept so bizarre it seems almost magical. Entanglement occurs when two or more particles become linked in such a way that their properties are no longer independent of each other. This link doesn't just mean they are in the same place at the same time, or that they are somehow communicating through normal channels. No, entangled particles can be separated by vast distances, and a change in one will instantly affect the other, no matter how far apart they are. This was famously described by Albert Einstein as spooky action at a distance, something that felt so impossible, even he struggled to accept it as real. But experiments have since confirmed entanglement, proving that particles can indeed remain connected across space in ways that defy our classical understanding. Now let's take this mind-bending idea and apply it to black holes, the most enigmatic objects in the universe. At first glance, black holes seem like the ultimate isolation points in space. Vast regions where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. They're the epitome of cosmic dead zones, swallowing everything that falls in and erasing any trace of it. At least, that's what we used to think. But as our understanding of quantum physics has deepened, scientists have begun to entertain a different, more complex picture. Some researchers propose that black holes might not be isolated after all. Instead, they could remain quantum entangled with the rest of the universe, even after swallowing matter. The idea is both fascinating and, for many, unsettling. If black holes retain a quantum link with the universe, it suggests that the boundary between the black hole and the outside world might not be as rigid as we once thought. Even after matter is pulled inside, the black hole could still be connected to the rest of reality in a hidden, quantum sense. In this scenario, the information of everything the black hole consumes doesn't vanish. Instead, it might remain encoded in the black hole's quantum state, subtly influencing and being influenced by the universe around it. Entanglement works in strange and complex ways, so it's important to understand the depth of the implications. If a particle is entangled with another, changing the state of one will cause an immediate change in the other. This isn't bound by the rules of classical physics, where information cannot travel faster than the speed of light. In the quantum world, entanglement allows for instant communication across distances that would otherwise seem impossible. Now imagine applying this concept to black holes. If a black hole remains quantum entangled with the universe, it means that even though it might appear like a one-way trap, it could still be subtly connected to the universe, carrying information to and from the rest of reality. This idea challenges everything we thought we knew about black holes. We always assumed that once something crosses the event horizon, it was gone for good, lost to the endless void. But what if it's not so simple? What if the information, or the essence of what was once inside the black hole, still exists in some form, quietly interacting with the universe in ways we don't yet fully understand? One of the leading theories that explores this connection is the holographic principle. This theory suggests that the information contained within a black hole might not be lost at all, but instead might be encoded on the event horizon in a two-dimensional form, like a hologram. This would mean that everything that falls into a black hole, including all of its physical information, could be preserved on the surface of the event horizon, but in a way that we can't yet access. Further research has suggested that the information might not just be preserved, but could also be shared through a quantum connection, a kind of whisper across space-time. Imagine a scenario where the black hole is still entangled with the surrounding universe, like a network of interconnected nodes in a vast cosmic web. The material that falls into the black hole while seemingly disappearing from our view, might still have a quantum relationship with the universe outside the event horizon. It's as though the black hole and the universe are exchanging information in a way that's hidden from us, like two people communicating through a veil of fog. This notion is bolstered by studies in quantum mechanics and the physics of black holes. According to the famous physicist Stephen Hawking, black holes emit radiation, now known as Hawking radiation, as a result of quantum processes happening near the event horizon. This radiation allows black holes to lose mass over time, and it's through this process that information about the matter inside the black hole might eventually escape, despite the black hole's immense gravity. The Hawking radiation isn't exactly the same as the information that originally fell into the black hole, but it suggests that black holes have a way of interacting with the outside universe that doesn't involve total isolation. One of the key questions in modern physics is whether this quantum entanglement between black holes and the universe could have broader implications. If black holes are indeed entangled with the cosmos in some way, they could play an important role in the structure and evolution of the universe. The interconnectedness of black holes with the space around them could influence everything from the formation of galaxies to the behavior of particles at the smallest scales. The fabric of reality itself might be more interconnected than we ever imagined, with black holes serving as nodes in a vast cosmic network. Some scientists even speculate that black holes might be more than just connectors of information. They could be essential to understanding the nature of time and space itself. In the same way that quantum mechanics describes a reality that's fundamentally different from the classical world, black holes might hold the key to unlocking deeper truths about the nature of existence. If they are entangled with the universe, they could be part of a much larger, more intricate system that governs how everything in the universe is related, from the smallest particles to the largest structures. For now, these ideas remain speculative, and we don't yet know how to test them with the precision that modern science requires. But the very possibility that black holes could be entangled with the universe opens up an exciting frontier for future research. It suggests that these cosmic giants, often seen as the ultimate symbol of isolation and destruction, might actually be deeply connected to the larger, more mysterious web of reality. If black holes are truly entangled with the universe, they might not just be passive objects. They could be active participants in the ongoing dance of cosmic evolution, interacting with the universe in subtle and profound ways that we're just beginning to comprehend. The more we learn about black holes, the more we realize that they might not be the dead ends of space that we once thought. Instead, they could be the gateways to a deeper, hidden level of understanding, a cosmic web in which everything is connected and nothing is ever truly lost. Memory without matter. When we think about memory, it's easy to picture something physical, perhaps a brain storing experiences in complex networks of neurons, or a book holding knowledge in inked pages. A computer chip, with its transistors, stores data in binary code, translating it into something usable. In all of these examples, memory is something concrete, something that relies on material objects to retain information. But when it comes to black holes, things are far less straightforward. These cosmic giants might defy the very idea of memory as we understand it. Rather than relying on a tangible medium like brain cells or circuits, black holes might store information in a way that's beyond our everyday experiences, without needing any matter at all. Instead of holding on to details in physical structures, black holes may record the information of everything they absorb through changes in space-time itself. This is a radically different concept from how we typically think of memory. Here, memory doesn't reside in a physical object. It's etched into the very fabric of the universe. The idea that black holes could store information without any matter involved is rooted in one of the more mind-bending aspects of modern physics, the interplay between gravity and quantum mechanics. According to the theory of general relativity, black holes warp space-time to such an extreme degree that anything that crosses their event horizon is pulled into a state of near infinite density. And yet, if we look closer at the finer details of this theory and at the nature of quantum physics, we find that these massive objects might do something far stranger than we thought. Instead of simply destroying everything they swallow, black holes might record and preserve the information, storing it in the subtle curvatures of space-time itself. At the heart of this idea is a theory known as holography, which suggests that the universe could function like a hologram, where information about three-dimensional objects might be stored on a two-dimensional surface. In the case of black holes, this theory implies that all the information about the particles and energy that fall into a black hole could be stored at its event horizon, the boundary beyond which nothing can escape. This might sound abstract, but think of it like a snapshot of every photon, every particle, and every bit of energy that passes through the event horizon. The black hole doesn't erase these details. Instead, it might encode them, with the information preserved in a kind of holographic form, where each little part of the event horizon holds a piece of the story. But this isn't the kind of memory we can interact with in a way we're familiar with. Unlike a book or a brain, where the information is laid out in a linear, organized way, the memory of a black hole is scattered across the fabric of space-time, encrypted in ways we don't fully understand. The details are there, but they are distorted by the intense gravitational forces of the black hole and potentially scrambled by the very nature of quantum mechanics. The concept of memory written into space-time itself ties into the intriguing field of quantum gravity, which attempts to reconcile the laws of quantum mechanics, which govern the behavior of the very small, with general relativity, which governs the behavior of the very large, like black holes. Physicists have long been trying to unify these two forces, and black holes might hold the key. The idea that information is preserved, even in the extreme conditions of a black hole, aligns with the principle of quantum unitarity, which suggests that the universe doesn't lose information, but instead transforms it in ways we don't yet understand. If this principle holds true, then black holes might not simply obliterate the past of everything they swallow. Instead, they might preserve it in a form we can't yet access. This notion was challenged by one of the most famous paradoxes in theoretical physics, the black hole information paradox. In the 1970s, physicist Stephen Hawking discovered that black holes can emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation leads to the gradual evaporation of the black hole over incredibly long timescales. The problem is that, according to traditional physics, once a black hole evaporates completely, all the information it absorbed would be lost forever. This posed a direct conflict with the principles of quantum mechanics, which assert that information cannot be destroyed. But more recent work has suggested that black holes might preserve information in ways we didn't expect. For instance, some scientists propose that instead of erasing everything it consumes, the black hole might encode this information in the radiation it emits. This radiation, when carefully analyzed, could hold the key to unlocking the mysteries of what happens to the information swallowed by black holes. Interestingly, the idea of memory in black holes might also be tied to something called the no-hair theorem, which states that black holes have only three observable properties: mass, charge, and spin. This theorem suggests that once an object enters a black hole, all the details of its identity, its shape, composition, color, and so on, are lost, leaving behind only these three simple properties. However, the challenge posed by the information paradox is that if black holes truly only retain these three properties, where does all the other information go? How can the black hole hold on to a complete record of the objects it consumes without erasing it? Some physicists believe that the key to resolving this paradox lies in understanding the quantum entanglement that occurs near the event horizon. Quantum entanglement is a phenomenon where particles become linked in such a way that the state of one particle is directly tied to the state of another, no matter how far apart they are. This suggests that black holes could be intricately entangled with the particles and energy they swallow, storing information in the way these particles are linked. The detailed memory of the swallowed objects could be encoded in the quantum state of the black hole, even though we can't see it directly. This view of black holes as cosmic memory keepers challenges our traditional understanding of how the universe works. Instead of being simple, static objects that destroy everything they touch, black holes might be dynamic, evolving systems that preserve and record the history of the cosmos. Their memories aren't like the ones we know, written in books or stored in our brains, but are woven into the very structure of space-time itself, in a form that's beyond our current ability to decode. In a sense, black holes could be the universe's most sophisticated record keepers, holding a complete history of everything that has ever fallen into them. The information they preserve might be encoded in a way so complex that it's impossible for us to understand it with today's science, but the implications are profound. Could black holes be holding the key to understanding the deepest mysteries of the universe? Could the information they store reveal secrets about the nature of space, time, and even consciousness itself? As we continue to probe the depths of black holes and the fabric of space-time, we are just beginning to glimpse the profound possibilities. The idea that memory could exist without matter, written in the very curves and folds of space-time, forces us to reconsider what we know about the universe and what might lie hidden, waiting to be discovered. Are black holes natural observers? In the strange and fascinating world of quantum mechanics, one of the most mind-boggling concepts is that nothing truly happens until it is observed. It sounds paradoxical, but it's a principle that has been confirmed time and time again in experiments. This idea comes from the famous thought experiment called the double-slit experiment, where particles like electrons behave differently when they are being watched. When no one is looking, these particles seem to take multiple paths simultaneously, but the moment an observer is present, they settle into a definite path. This idea challenges our fundamental understanding of reality. How can something be in two places at once, or behave as a wave and a particle, only to decide what it is when we look at it? What does it mean for the universe if everything relies on an observer? And most importantly, what exactly is an observer? The concept of observation in quantum mechanics isn't as simple as it might sound. It's not just about a conscious being watching something happen. It's more about the interaction between the system and the environment, and how that interaction forces the system to choose a state. This brings us to a very intriguing question. Could there be natural observers in the universe? And if so, could black holes themselves act as these natural observers? At first glance, the idea of a black hole being a watcher seems odd. After all, black holes are famously known for their mysterious nature. They are regions of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. They are often described as the cosmic vacuum cleaners, pulling in anything that gets too close, including gas, dust, and even entire stars. So how could something so destructive and isolated be involved in the act of observation? Let's take a closer look. In quantum mechanics, the act of observation seems to play a fundamental role in determining the behavior of particles. A particle, like an electron, doesn't have a definite position or momentum until it's measured. It exists in what we call a superposition of all possible states until it is observed, at which point it collapses into a single state. But this measurement doesn't require a conscious observer. It's the interaction of the particle with its environment that causes this collapse. This brings us to black holes, which are extreme environments in space where the laws of physics are pushed to their limits. A black hole's event horizon, its boundary, marks the point beyond which nothing can return. Once something crosses this line, it's lost to the black hole forever. However, the process by which objects and energy fall into a black hole is fascinating. As matter gets pulled toward the black hole, it gets heated up and emits radiation, a phenomenon known as Hawking radiation. This is not just a one-way interaction. Black holes are constantly reacting to everything they absorb. This reaction might be the key to understanding black holes as natural observers. In quantum mechanics, the process of measurement happens when a system interacts with its environment, and in the case of a black hole, the environment is everything that falls into it. Every bit of matter or energy that crosses the event horizon contributes to the black hole's properties. The black hole reacts by increasing its mass, and the information about what has fallen in is imprinted onto the black hole's surface in the form of what's known as the black hole entropy. The idea that black holes could be acting like natural observers comes from the fact that their very existence forces events to be locked into a definitive state. Every piece of matter that enters a black hole adds to its overall mass and alters its characteristics. Just as in quantum mechanics, where an observation forces a system to settle into one state, the black hole's reaction to what it absorbs may freeze the information about the system, locking it into a specific configuration in the black hole's history. This could be thought of as the black hole remembering the events that happened around it, even though the information is now beyond reach. But what does this mean for the universe? If black holes are, in some sense, natural observers, this could imply that the universe itself is being observed in a way that we never considered before. Every time something crosses the event horizon of a black hole, it's as though the black hole is taking a snapshot of the universe. It's not observing in the traditional sense, but rather in the way that a computer stores data, simply by reacting to the information that's fed into it. This idea raises another intriguing point. The black hole's reaction to matter might be linked to the so-called information paradox. According to quantum mechanics, information about a system should never be lost. However, once something crosses into a black hole, it seems to vanish, which creates a puzzle for physicists. How can the information about what fell into the black hole be recovered if it can never escape? The resolution to this paradox may lie in the way black holes observe the universe. Instead of losing information, black holes could be storing it in some form on their event horizons, and in doing so, they are participating in the act of measurement by preserving that information for future study. This also connects to the holographic principle, a theory that suggests the entire universe might be encoded on the surface of a black hole. According to this principle, the information about everything in the universe could be stored at the edge of a black hole, where it might be observed and accessed. If black holes are natural observers in this sense, it would mean that the fabric of space-time itself is being influenced by these massive objects. They might be the key to understanding the way the universe unfolds. However, we must be cautious not to overstate the role of black holes as observers. While their gravitational pull and their ability to absorb information are undeniable, they do not see or understand in any conscious sense. They simply react to the matter and energy they encounter. The universe, in this interpretation, could be seen as a giant recording device, where every interaction, no matter how small, leaves a mark on the cosmic fabric. So, while black holes may not be conscious observers in the way we might imagine, they could indeed play a crucial role in determining the evolution of the universe. By absorbing matter and reacting to the energy around them, black holes may be forcing events to freeze into a particular state. In much the same way, quantum measurements force particles to choose a position or momentum. Their influence on the universe might not be in the form of watching, but in the way they affect everything around them. In this sense, black holes might be the ultimate witnesses of cosmic history, not observers with emotions or opinions, but silent, mechanical entities that enforce the laws of physics simply by existing. Their very presence might shape the way the universe evolves, locking information into the structure of space-time and ensuring that the past is preserved in the form of their reaction to everything they absorb. This idea challenges our traditional notions of observation and measurement. In quantum mechanics, the observer is often seen as an external force, that causes the system to collapse into a definite state. But in the case of black holes, the observer is not external. It's an intrinsic part of the system itself. Black holes could be the ultimate example of how the universe might remember the past, not through consciousness, but through the physical consequences of their actions. In the end, while black holes might not be conscious observers in the way we understand, their role in shaping the universe could be far more profound than we ever imagined. They may not just be passive consumers of matter and energy. They might be the cosmic recorders, locking the events of the universe into the very fabric of space-time, preserving the history of the cosmos for as long as they exist. Cosmic censorship and the hidden mind. The universe, with all its awe-inspiring phenomena, still has its secrets, some of which may be forever out of our reach. Among the most profound of these mysteries is the concept of cosmic censorship, a rule that suggests nature hides its most extreme events behind the event horizon of black holes. This idea, first proposed by physicist Roger Penrose in the 1960s, is a key part of our understanding of black holes. According to this rule, when matter collapses to form a black hole, the singularity, the point of infinite density at its core, is hidden from view. No one can observe what's happening there. It's as if the universe has drawn a veil over the most chaotic, complex processes occurring in the depths of space. Cosmic censorship, at its core, asserts that the singularity at the heart of a black hole is shielded, hidden from the outside universe by the event horizon. This boundary marks the point of no return. Once something crosses the event horizon, it cannot escape, not even light. It's a region where space and time are stretched and warped to extremes, and where the laws of physics, as we know them, begin to break down. But there's something about this idea that still stirs curiosity and raises important questions. What if the reason for this cosmic censorship isn't just to protect us from the violent and incomprehensible nature of black holes? What if it's something deeper, something more fundamental about the very nature of the universe? One could speculate that the universe doesn't just hide black holes for safety reasons. Maybe it's to preserve the complexity within them. In a way, it could be that black holes act like the skull protecting the brain. Just as the skull encases and shields our mind from harm, perhaps the event horizon of a black hole serves as a barrier that shields the intricate and far-reaching processes occurring inside. These processes, hidden from our view, could be far more complex than we can even begin to imagine. To understand this idea better, it's helpful to consider the remarkable features of black holes themselves. A black hole isn't just a region in space where gravity is so strong that not even light can escape. It's a place where the fabric of space-time is stretched and distorted to such extremes that the usual laws of physics seem to lose their meaning. The singularity at the center of the black hole is where all the mass of the black hole is concentrated, and its gravitational pull is infinitely strong. But the singularity isn't something we can observe directly. It's hidden behind the event horizon, a boundary that marks the point beyond which nothing can return. This barrier keeps the most extreme and complex behaviors within the black hole concealed from the outside world. The event horizon, in a sense, serves as a kind of cosmic firewall, keeping everything that happens inside hidden from view. But this doesn't mean that the black hole is a simple or static object. Quite the opposite. The behavior inside a black hole could be much more complex than we can comprehend. It's easy to think of a black hole as an object that simply sucks everything in and doesn't give anything back. But what if there's far more to the story? The universe might be using the event horizon as a way to protect the complexity of what's happening inside the black hole. After all, a black hole isn't just a vacuum. It's a place where space-time is severely warped, where matter is compressed to unimaginable densities, and where even the most fundamental laws of physics are stretched beyond their limits. It's not just an extreme environment. It's an environment in which new, unknown physical processes could be occurring. These processes might involve the very nature of gravity, quantum mechanics, and space-time itself. Perhaps the event horizon isn't just a barrier to protect us from the destructive forces of a black hole. It's a way to preserve the strange, complex behaviors that occur within. The analogy of the skull and brain is a useful one. Just as the skull protects the brain from physical harm, the event horizon may be protecting the unknown, intricate processes within a black hole from being disturbed or observed. The brain, after all, is a place where countless neurons fire in a highly coordinated fashion, creating consciousness, thought, and awareness. If we were to somehow gain access to that hidden inner world, we might begin to understand how consciousness works, or even unravel the mysteries of how the brain processes information. Similarly, inside a black hole, there may be processes so complex and fundamental that they could change our understanding of the universe itself. This is, of course, speculative. We don't yet know what happens inside a black hole. In fact, the singularity at the center of a black hole is one of the greatest mysteries in modern physics. At this point, we can only infer what might be happening based on our understanding of general relativity and quantum mechanics. However, the idea that the universe might be shielding us from the extreme complexity within black holes raises intriguing possibilities. It suggests that there might be a level of sophistication within these objects that we're not yet equipped to understand. So what could be happening inside a black hole? One idea is that the forces of gravity at play within a black hole could be so intense that they influence the fundamental nature of space and time itself. In the highly curved space-time of a black hole, time might behave in strange and unexpected ways, potentially allowing for new physical phenomena. Another possibility is that the extreme conditions inside a black hole could give rise to new forms of matter or energy, forms that exist only in these extreme environments. We also know that black holes might be key players in the study of quantum gravity, as they sit at the intersection of general relativity and quantum mechanics, two of the most powerful theories in physics. Yet another fascinating possibility is that black holes could be related to some of the deepest questions in cosmology. Could the inside of a black hole provide insight into the origins of the universe itself? Could they hold the key to understanding the mysterious dark matter and dark energy that make up most of the universe's mass? These are questions we can't yet answer, but the potential is there. The event horizon, by hiding the most extreme and complex behaviors, might be shielding us from information that could revolutionize our understanding of physics and the universe at large. As we continue to probe the mysteries of black holes, we may find that cosmic censorship isn't just about protecting us from the destructive forces of these objects. Perhaps it's a safeguard that preserves the complexity and wonder of the processes happening inside. The universe may be hiding more from us than we realize, and it may be doing so for reasons we are only beginning to understand. In the end, black holes are far from simple objects. They are the ultimate test for our understanding of the laws of physics, and they are places where the fabric of the universe is stretched to its limits. Cosmic censorship, by hiding the singularity inside the event horizon, may not just be a rule for safety, it could be a way of preserving the complexity and intricacy of the universe itself. If we ever do find a way to peer inside a black hole, we might discover that there's far more going on than we ever imagined. Black holes and time distortion. Imagine standing on the edge of a vast, invisible boundary. You can feel the pull of something immense, something that bends the very fabric of space and time around you. It's a black hole, one of the universe's most mysterious and mind-bending phenomena. Black holes have fascinated scientists and stargazers alike for centuries. They are regions in space where gravity is so strong that nothing, not even light, can escape their grasp. But what's truly mind-blowing is not just their ability to trap everything in their vicinity. It's how they bend and stretch time itself. Time, as we understand it, is a constant, ticking forward in a predictable manner. We measure it in seconds, minutes, and hours. But near a black hole, this basic concept begins to unravel. The closer you get to the event horizon, the point beyond which nothing can escape, the more distorted time becomes. This distortion happens because of the extreme gravity around black holes, which warps space-time itself. As you approach a black hole, time doesn't flow at the same rate that it does far away from it. From the perspective of someone far from the black hole, you would appear to move slower and slower the closer you get to the event horizon. If you were to fall into the black hole, it would seem to those observing from a distance that your fall slows to a crawl. In fact, as you near the event horizon, it would appear to freeze completely, never quite crossing into the black hole. It's an effect that's purely the result of the extreme gravity bending time. However, from your own perspective, as you fall inward, time would feel normal. You wouldn't notice anything unusual about the passage of time, even though your perception is fundamentally different from someone watching from a safe distance. You'd experience seconds, minutes, and hours like usual. But the moment you pass the event horizon, you're entering a new realm where space and time no longer obey the same rules. This phenomenon, known as time dilation, is a direct consequence of Einstein's theory of general relativity, which describes how gravity can bend the fabric of space-time. According to this theory, massive objects like black holes warp space-time in such a way that time flows differently, depending on how close you are to the object. Near a black hole, time itself is stretched and distorted by the immense gravitational field. To someone far away, you'd seem to age more slowly, experiencing what feels like mere seconds, while years or even centuries might pass outside. The deeper you fall into the black hole, the more extreme this time distortion becomes. But it's important to note that, in reality, the passage of time for someone falling in is relative to their surroundings. So if you fell in, you might experience what feels like a normal journey, but it would appear to someone observing you from a distance that your motion was incredibly slow. It's an example of how relative time is when you enter regions where gravity has such a powerful effect on space-time. The most fascinating question raised by this phenomenon is what might be happening inside the black hole. If time is stretching to such an extreme degree, could the black hole itself be processing information in a way that we cannot fully comprehend? Is the time dilation around black holes a kind of slow, cosmic thinking, where the process of matter and energy folding inward might unfold like a thought stretched across eons? Think of it this way. We experience time in a linear fashion, moving from one moment to the next, but near a black hole, the flow of time becomes disconnected from our normal understanding. What seems like an infinite stillness to an outside observer may in fact be a slow, unfolding process within. Could this stretching of time allow for something like thought to occur over vast periods? Is there a way that the black hole, with its complex interactions of matter and energy, could think, in a sense, processing information at a pace we cannot begin to grasp? This isn't to suggest that black holes are consciously thinking in any human sense, but it does highlight a very strange possibility, that the nature of time itself, when stretched to the limits by the immense gravity of a black hole, could allow for processes to unfold at a pace that feels incomprehensible. What seems like silence from the outside might actually be a slow unfolding of events on a cosmic scale. We're left with more questions than answers. The truth is, even with the advances in physics and our understanding of general relativity, we still don't fully understand what happens inside a black hole. The singularity, the point at the very center of the black hole, remains a mystery. It's a place where matter and energy are crushed into infinite density, and the laws of physics, as we know them, break down completely. No information can escape from a black hole beyond the event horizon, so it's impossible to gather data from inside. But that doesn't mean we don't learn from studying the outer regions. The study of time dilation around black holes has already provided valuable insights into the way gravity affects space-time. It's a key feature in understanding how the universe operates at the largest scales. And as we continue to refine our telescopes and observational tools, we'll be able to study black holes in even more detail, unraveling some of the deepest mysteries in astrophysics. Perhaps one day, we'll come to understand more fully how black holes process time and how their unique properties might relate to the very nature of the universe. Until then, we can only speculate about the strange, slow passage of time that occurs near these cosmic giants, where what feels like a moment could actually stretch across an eternity. In the end, black holes remind us that the universe operates on scales far beyond our everyday experience. They force us to confront the limits of our understanding, to challenge what we think we know about space, time, and reality itself. Time may seem like a constant, but near a black hole, it becomes a fluid and malleable thing, something that bends and stretches, holding secrets that are just beyond our reach. And perhaps, in those secrets, we'll one day find answers to some of the universe's most profound questions. As we continue to explore the cosmos, one thing is certain: the mysteries of black holes are far from over, and every discovery brings us one step closer to unraveling the deeper truths of the universe. Complexity beyond life. When we think about complexity, we often tie it to life. After all, the most intricate systems we know, from the vastness of ecosystems to the workings of the human brain, seem to emerge from living organisms. But what if complexity isn't solely the domain of life itself? What if it's a fundamental property that exists throughout the universe, even in places where life has never had a chance to form? The more we explore the cosmos, the more we see that complexity can arise in the most unexpected places, without any need for life to create it. Take weather systems, for instance. Every storm, every shift in atmospheric pressure is a reflection of intricate processes unfolding. Winds swirl and collide, moisture condenses and evaporates, and temperatures fluctuate. Despite this chaos, weather systems maintain an incredible level of organization. Predictable patterns emerge from the apparent randomness. Cyclones spin with remarkable precision. The global jet stream moves in such a way that it shapes the entire planet's climate. None of this complexity requires life. It's simply the result of natural forces interacting in a system that happens to be governed by complex physical laws. Now, step even further out into the universe. Galaxies, vast collections of stars, gas, and dust, follow patterns that are nothing short of remarkable. Some of these galaxies spiral, twisting around a central point in a graceful, almost elegant dance. Others cluster together in groups, bound by the invisible threads of gravity, forming superclusters of galaxies. The interactions within and between galaxies create a kind of universal choreography that seems to emerge from the very fabric of space-time itself. Even when we look at something as massive as a galactic collision, there's a structured chaos to it, a fine balance between destruction and creation, as new stars form out of the turmoil. Once again, no life is needed to produce such complexity. It's simply the interplay of forces on an unimaginable scale, governed by gravity, light, and the motion of matter. Then there are star clusters, another example of complexity unfolding without the need for life. These clusters, tightly bound groups of stars, are born out of the same forces that govern galaxies. Over time, the stars within them interact, sometimes violently, sometimes gently. The result is a dynamic, ever-changing system where stars are born, die, and interact in ways that shape the cluster's future. The birth of a new star is the culmination of immense forces of pressure and heat, a process that begins with the gravitational collapse of a cloud of gas and dust. From this collapse, matter is compressed to the point where nuclear fusion can occur, and a star ignites. In a star cluster, all of this happens within a confined space, creating a stunning level of organization and complexity without a single living thing involved. But what if these patterns, these systems, go beyond what we can currently perceive? What if there's something deeper at play, something fundamental to the very nature of the universe itself? Could it be that complexity is not just a byproduct of life, but a universal characteristic that emerges naturally when conditions are right? Some scientists and thinkers have even suggested that complexity could be a property of the universe, something that exists at all scales, from the tiniest particles to the largest galaxies. It's an intriguing idea, one that hints at the possibility that consciousness, or at least something like it, might not be as rare as we think. Consider the possibility that consciousness isn't something exclusive to living organisms. For centuries, we've defined consciousness as something that arises from the neural activity within brains, something that only occurs when biological systems reach a certain level of complexity. But what if consciousness, in some form, could exist in non-living systems too? What if it's not tied to biological brains at all, but to the very nature of complex systems? The more we learn about the universe, the more it seems that complexity, in all its forms, has a kind of self-organizing property. It finds ways to create order out of chaos, to give rise to new structures, and to evolve over time in unpredictable yet beautifully intricate ways. Could this process of self-organization be a kind of universal consciousness, not confined to living things, but present in the very patterns and structures of the cosmos? At the most extreme end of this question lies one of the most fascinating and mysterious objects in the universe, the black hole. When we think of black holes, we often picture them as the ultimate destroyers of matter, regions of space where gravity is so intense that nothing, not even light, can escape. But black holes are also the ultimate expression of complexity. They are the result of the collapse of massive stars, a process that concentrates an enormous amount of mass and energy into an infinitely small point, creating a singularity. Around this singularity, the fabric of space-time is warped to such an extent that it creates a boundary, known as the event horizon, beyond which nothing can return. Yet despite their destructive nature, black holes are also places of creation. They are responsible for some of the most energetic phenomena in the universe, such as quasars and gamma-ray bursts, which are among the most powerful events known to man. The complexity of black holes doesn't just lie in their physical properties, it also lies in their role within the broader cosmic ecosystem. As black holes consume matter and grow, they play a crucial role in shaping galaxies. The gravitational pull of a supermassive black hole at the center of a galaxy can influence the formation of stars and the behavior of the galaxy itself. In this way, black holes act as both creators and destroyers, constantly reshaping the universe. They are, in many ways, the ultimate expression of the universe's natural drive toward complexity, where the laws of physics push matter and energy to their absolute limits. In a way, black holes challenge our understanding of the universe and its laws. They remind us that complexity isn't just something that arises from life or biological processes. It's a fundamental feature of the cosmos itself. Whether it's the formation of galaxies, the birth of stars, or the behavior of black holes, the universe seems to have a natural tendency to create intricate and beautiful patterns, often beyond our ability to fully comprehend. In this sense, black holes are a reminder that complexity is a universal force, one that exists on every scale, from the tiniest particle to the most massive objects in the universe. Perhaps when we look at the cosmos, we're seeing more than just the remnants of ancient stars or the aftermath of cosmic collisions. Maybe we're seeing the universe itself, organizing itself in ways we're only beginning to understand. And perhaps in that complexity there's a kind of universal intelligence not tied to any specific form or place, but embedded in the very fabric of the universe. It's a thought-provoking idea, one that suggests that complexity, in all its forms, could be the key to understanding not only the universe, but also our place within it. The fuzzball hypothesis. In the strange, enigmatic world of black holes, we have long held a certain view. Black holes are dead zones. These massive objects in space are believed to swallow everything in their path, from light to matter, with no chance of escape. For a long time, scientists have viewed black holes as points in space where the laws of physics break down entirely. They were the ultimate enigma in our universe, hidden from view behind an event horizon, a boundary beyond which nothing could return. But in recent years, a radical and exciting idea has emerged. What if black holes aren't dead zones at all, What if instead they are teeming with life at the most fundamental level? This idea is encapsulated in something known as the fuzzball hypothesis, a concept that challenges our traditional understanding of black holes. The fuzzball hypothesis suggests that black holes might not be empty pits of nothingness, as previously thought. Instead, they could be massive, dense structures made up of tangled webs of microscopic strings, constantly vibrating and shifting in complex patterns. This idea comes from a more modern theory in physics called string theory. String theory posits that, at the smallest scales of the universe, everything, every particle and force, is made up of tiny, vibrating strings rather than point-like particles. These strings vibrate at different frequencies, and depending on how they vibrate, they give rise to the various fundamental particles that make up our universe. In the context of black holes, string theory suggests that these tiny, vibrating strings could be the very fabric of what makes up the black hole itself. Imagine, then, a black hole not as a lifeless void, but as a dynamic, swirling ocean of these microscopic strings, instead of a singular dense point at the center, as we traditionally think of a black hole. There's an entire realm of activity, an intricate tangle of strings constantly interacting with each other. This is what the fuzzball hypothesis proposes. It suggests that a black hole could be more like a fuzzball, where all these strings are tightly packed together, creating a dense, chaotic ball of activity. At the smallest scales, this structure would be a place of constant, unpredictable motion. The strings would vibrate and shift in a sort of microscopic storm, with patterns emerging and vanishing in the blink of an eye. It's a place of endless change, where no two moments are ever quite the same. The idea is that this ever-changing landscape is fundamentally different from the way we traditionally imagine black holes. Instead of being a simple, static point of no return, a fuzzball could be a highly dynamic, ever-evolving structure. The fuzzball hypothesis could also provide a solution to one of the biggest puzzles surrounding black holes, the so-called information paradox. According to classical physics, once something falls into a black hole, it's lost forever, including all the information about that object. This has been a long-standing problem for physicists, as it seems to violate the fundamental laws of quantum mechanics, which assert that information must be preserved. But the fuzzball hypothesis offers a potential resolution. If a black hole is not a singular point of no return, but instead a complex, vibrating structure of strings, then the information of objects that fall in could be encoded in the strings themselves. Rather than being lost forever, the information could be preserved in the chaotic dance of strings that make up the fuzzball. This idea, while still theoretical and far from being proven, offers an intriguing glimpse into a radically different way of thinking about black holes. It suggests that black holes could be alive with activity, rather than being dark, empty voids. It also opens up new possibilities for understanding the relationship between gravity, quantum mechanics, and the fundamental building blocks of the universe. In this new view, the black hole is not a death sentence for information, but a place where the most fundamental processes of the universe play out in complex and unexpected ways. However, there's still much to be learned before we can fully embrace the fuzzball hypothesis as a valid model of black holes. The idea is still very much in its infancy, and many questions remain unanswered. How exactly do these strings behave at the event horizon? What happens to them at the singularity, the point of infinite density at the center of the black hole? And how can we test this hypothesis, given that we can't directly observe the inside of a black hole? These are all questions that scientists are still grappling with, and it will likely take years, if not decades, of research and observation to get closer to the answers. But despite the many unknowns, the fuzzball hypothesis offers an exciting new avenue of exploration. It invites us to think about black holes in an entirely different way. Instead of seeing them as simple, lifeless objects, we can start to imagine them as complex dynamic systems, filled with the vibrations and interactions of strings. In this view, black holes are no longer just regions of space where the laws of physics break down. They are places where the most fundamental forces of nature come together in a complex dance, revealing new aspects of the universe that we have yet to understand. In a way, the idea of black holes as fuzzballs challenges our basic assumptions about what it means for something to be alive or active. While we typically associate these qualities with biological systems, the fuzzball hypothesis suggests that even the most extreme objects in the universe might display behaviors that are far more complex than we originally imagined. In this new view, black holes might not just be places of destruction, they could also be places of creation, where the very fabric of the universe is constantly being reshaped. Ultimately, the fuzzball hypothesis raises profound questions about the nature of reality itself. If black holes are indeed made up of these microscopic vibrating strings, it could point to an entirely new understanding of space, time, and the fundamental structure of the universe. The idea of a fuzzball might sound far-fetched at first, but in the world of modern physics, strange and unexpected ideas are often the ones that lead to breakthroughs. Only time will tell whether the fuzzball hypothesis will become a cornerstone of our understanding of black holes, or whether it will be another fascinating idea that eventually fades away. For now, though, it serves as a reminder that the universe is full of surprises, and there is still so much left to explore. Black holes as cosmic mirrors. Black holes have long been one of the most mysterious and intriguing phenomena in the universe. Traditionally, they were viewed as objects that consumed everything in their path: light, matter, and even time itself. We understood black holes as regions where gravity is so intense that nothing can escape their grasp, not even light. But recently, a new perspective is emerging, suggesting that black holes may serve as much more than just cosmic traps. They might also act as mirrors, reflecting the very structure of the universe in ways we are only beginning to comprehend. For decades, scientists have grappled with the true nature of black holes, seeking to understand how they function and how they fit into the broader cosmic puzzle. We've known for a long time that they are formed when massive stars collapse under their own gravity, creating a singularity, a point in space where the laws of physics as we know them seem to break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. But while black holes have been studied extensively for their gravitational pull and their role in shaping the evolution of galaxies, their true significance may go much deeper. What if black holes aren't just regions of death and destruction? What if they are instead key players in the unfolding drama of the cosmos, acting as mirrors that reflect the deepest secrets of existence itself? In recent years, theoretical physicists have begun to speculate that black holes might reflect something fundamental about the nature of the universe, something far beyond their role as gravitational vacuum cleaners. One of the most intriguing ideas is that black holes could be reflections of the universe's underlying structure, offering insights into the fundamental properties of space, time, and information. This theory builds on the idea that the universe itself might be a vast, interconnected network of information, where every particle, force, and interaction is encoded and stored in the fabric of space-time. According to this view, everything in the universe, whether it's the motion of galaxies, the behavior of subatomic particles, or even the flow of time itself, is a form of information. This information is constantly shifting and evolving, much like a dance of data that shapes the universe's evolution. What makes black holes particularly interesting in this context is the way they seem to process and store information. As objects that distort space-time to an extreme degree, black holes challenge our understanding of physics in profound ways. The idea that they might reflect the information of the universe isn't just a theoretical notion. It's rooted in some of the most cutting-edge research in physics. One of the key pieces of evidence for this idea comes from the study of the so-called information paradox associated with black holes. According to classical physics, once something crosses the event horizon of a black hole, it is lost to the universe forever. But this doesn't sit well with quantum mechanics, which suggests that information cannot be destroyed. This apparent contradiction has led to intense debates among physicists about whether the information contained within matter that falls into a black hole is truly lost, or if it is somehow preserved. The breakthrough came when researchers began to investigate the so-called holographic principle, an idea first proposed in the 1990s by physicist Gerard 't Hooft. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space. In other words, the three-dimensional universe we experience might be a projection of information encoded on a two-dimensional surface, much like a hologram. This idea has profound implications for understanding black holes. According to some theorists, the information that falls into a black hole might not actually be lost. Rather, it could be stored on the event horizon in some form of quantum information. This concept is further supported by the work of physicist Juan Maldacena, who proposed the adds over CFT correspondence, a theoretical framework that suggests a deep connection between gravity in a higher dimensional space and quantum field theory in a lower dimensional space. This idea has led to the suggestion that the interior of a black hole might be encoded on its surface, turning it into a kind of cosmic mirror that reflects the deeper structure of space-time itself. So, what does all this mean? It suggests that black holes may not simply be destructive forces, as they have often been portrayed. Instead, they could be repositories of information, encoding the fundamental properties of the universe. They might serve as cosmic mirrors, reflecting the flow of information across the entire cosmos, capturing the essence of reality itself. In this light, black holes could be seen as not just the end points of matter and energy, but as windows into a deeper layer of existence. They might reveal the fundamental interconnectedness of all things, the way that information, energy, and matter are woven together in the fabric of space-time. By studying black holes, we could be looking at mirrors that show us something profound about the universe, a giant, endless dance of information, memory, and change. This idea aligns with the growing realization in physics that the universe itself might be fundamentally informational. In recent years, scientists have increasingly turned to the concept of quantum information theory to understand the behavior of particles and forces at the smallest scales. Rather than thinking of the universe as a collection of physical objects, researchers are beginning to view it as a system of information processing. This shift in perspective could help explain some of the most puzzling aspects of the cosmos, from the behavior of black holes to the mysterious nature of dark matter and dark energy. In this sense, black holes might not just be reflecting light or matter, they could be reflecting the very structure of the universe. They could be mirrors that show us the intricate dance of information that underlies everything in existence. And as we continue to study these enigmatic objects, we might begin to unravel some of the deepest mysteries of the cosmos. Perhaps in the end, black holes are not just strange and unfathomable objects in space. They could be a crucial piece of the cosmic puzzle, offering us a glimpse into the true nature of reality. If black holes reflect the fundamental structure of the universe, then studying them might bring us closer to understanding the very fabric of existence. They could be mirrors not just reflecting the past, but showing us hints of the future, of a universe that is awake in ways we are only beginning to imagine. As we continue to explore the mysteries of black holes, we may find that they hold the keys to unlocking some of the most profound questions about the nature of space, time, and existence. And in doing so, we might come to realize that the universe itself is far more alive, interconnected, and dynamic than we ever could have imagined. Black holes, as cosmic mirrors, may reveal to us a reality that is both more mysterious and more beautiful than we could have ever dreamed. As we've explored the mystery of black holes, we've come to see them in a new light. What were once thought to be cosmic destroyers might be the universe's most dedicated record keepers, preservers of everything that has ever existed. They hold something deeper than mere destruction: memory, woven into the very fabric of space-time. But what does it mean for black holes to carry the universe's story? To think of them as holding information, not just from the stars that collapsed into them, but from everything, every speck of matter, every moment in the cosmic history. Here's the most mind-bending idea of all. What if black holes aren't just remnants of dead stars? What if they aren't the universe's ultimate trash cans, pulling in everything and letting nothing escape? Instead, what if they are the universe's most powerful proof that nothing is ever truly lost, that even in the darkest corners of the cosmos, nothing disappears completely? Could it be that black holes are more than just invisible objects? Could they be silent witnesses to everything that has ever happened? The more we learn about them, the stranger they seem. These cosmic giants might not be conscious in the way we understand mind or awareness. They don't experience joy, pain, or fear. But maybe, just maybe, they're carrying something else. The story of the universe, encoded within them, slowly unraveling one particle at a time. Their connection to the universe is not just gravitational, but might be linked to the strange, invisible threads of entanglement that tie everything together. And if black holes can hold so much without a mind, it challenges everything we think we know about consciousness. What if mind itself isn't some rare phenomenon, unique to a few beings on this tiny planet of ours? What if it's everywhere, woven into the very fabric of reality, tangled into gravity and space-time, humming in the silence of the universe? The idea that consciousness could be more fundamental than we realize, that it might even be a natural part of the universe itself, opens up an entirely new way of thinking about life, awareness, and memory. When we peer into the depths of a black hole, we're not just staring into emptiness or destruction. We might be looking at the universe's deepest and oldest records, so slow, so alien, we barely notice them. And though they appear to be silent, they might be thinking in a way we can't yet comprehend. It's as if they're holding on to everything, patiently waiting to tell us the stories they've witnessed. So, as we wrap up our journey, it becomes clear, black holes are not the ultimate erasers of existence, but rather the quiet preservers of it. They show us that memory doesn't need a brain to exist, that complexity and awareness can arise even in the most inhospitable places, and that life might not always look like we expect. These cosmic giants remind us that the universe is not just full of stars, planets, and light. It is full of hidden stories, echoes of the past, and perhaps even minds, hidden and waiting for us to understand. If you enjoyed this video, leave a comment below and let us know what fascinates you the most about black holes. And if you haven't already, consider leaving a like and subscribing to the channel to stay updated on all our space explorations. Thanks for watching, and keep reaching for the stars.